Hello. All right, so today we're going to start something new in science, and we're going to talk about sound. So we've been talking. I don't know why I turned that off. We've been talking about energy, okay? And so sound is a type of energy, and we've talked about that. But now we're going to talk about sound a little more in depth, okay? All right. So we are going to talk about sound waves and what exactly is sound. So I'm going to start with just saying sound. So remember that if I'm writing in these videos, you also need to be. That way you can come back to these videos and study them, use them with your work that you do, and help you. Okay. Unless I say don't use your notes, you can use your notes. All right. So sound, like we said, is a form of energy. And I'm sorry about the video in the background. My daughter is watching. She just got home from the babysitters and she was watching a TV show, so I can do this real quick. Okay. Sound is made and transmitted by vibrating matter. So what that means is that sound has to have matter. It has to have matter to bounce off of and to use, okay? Sound sound is transmitted by vibrating matter. Okay? All right, so sound comes out as waves. All right, so this might be a little bit of writing, okay? So I'm just warning you now. So sound is compression waves. Sound travels in compression waves. So if you've ever played with a slinky, I'll show you a picture. I have one, but my daughter ruined it. So I had to order another one that we'll use in a couple days. I think on tomorrow. I can't remember. Okay, so this is a slinky. So it is like a spring, but it's called a slinky and it can go back and forth. So a slinky, that's like a compression wave because you can bunch it up or you can make it bigger. Okay, and that's how sound waves travel. Sound waves moves out. So sound waves move in all directions. We will talk about light next. And light moves in one direction, but sound moves everywhere. So it's just like you're able to hear Evelyn's TV. But if because of the sound waves, so sounds, you can hear her TV because of her sound waves, or the TV sound waves. So even though that's in the next room, you're still able to hear it because the way the sound uses matter, and all air has matter, it uses that to travel. But then if you think about light, which I know we're not talking about light, but they're sort of similar. Okay, so I have my flashlight on, okay, and it's shining that direction, right? If I put my hand here, there's no light. If I put my hand here, there's no light. But if I put my hand right here, there's the light. It's not behind, but it's coming out this way. So light travels from their direction and out, but sound travels in all directions. Okay, so sound waves. So let's go back up here to compression wave. I sort of forgot to add this. So when you see a sound wave, and we'll watch Dr. Bill. No, Bill Nye the Science Guy, and he'll talk about sound waves. Because I do love me some Bill Nye, and we'll talk about it there. All right, so this is called compression. This is when they bunch up. And then when they let loose, it's called refraction. Okay. All right, so a wave has different parts to it. And even like a wave at the beach, there are different parts to a wave. So you have from here to here is a wavelength. Okay. And then this is the bottom part of the wave, and this is called a trough. And then this is the top part of the wave, and it's called the crest. If you've ever been to the beach, the waves crest at the very top. Okay. So frequency is how low or high the sound waves are traveling. If you have a high frequency, you have a higher wavelength. So frequency okay. So the frequency is how high or low the pitch of a sound is. So if you speak with a low voice, the wavelength is low. See how there's so much distance between the wavelengths? Okay. And it's a lower sound. But if you speak with a higher wavelength, what are you doing? If you speak with a higher wavelength, like, hello, this is Miss Connor, then they're going to be more bunched up. Okay. So that would be a higher sound. Okay. The vibrations are more. All right. So let's, again, if you need to pause because I'm moving too fast, do it. Okay. So sound waves travel best in solids because they move more closely together. So if you think about how tightly it's supposed to be solids, but that does not. If you think about how closely the matter is in solids, you're able to hear sound waves move faster in solids. Okay, so if I don't have any my tuning fork, but I'll do that in another video. But so solids have the best sound. Okay. But then they move slowly. They lose a lot of their oomph in gases. And liquids, it's sort of hard for sound to travel. If you've ever talked underwater at the pool, you can still hear underwater, but the best way to hear is through solids. Metal, to be for sure. But gases is the slowest. Evan, can you go into the other room, please? Okay. So let's see. Oops. Well, I was going to try to pause the video, but I can't. Okay. I think I'm just using my old. Oh, this is important. Sound does not travel through space. Sound does not travel through space because there's no matter in space. Okay, so if there's no matter in space, space doesn't have anything to travel through. Sound doesn't have anything to travel through. Sound has to have a medium, and a medium means like something to go through. It has to have something to use. Well, I'm trying to not make that look sloppy, but ended up sloppy. Okay, so sound doesn't travel through space because there's no matter in space. There's no air. So if there's no air, there's no way that matter can travel in space. All right, I want to say a couple more things, and then we are done. So musical instruments, which are SOL, we talk about musical instruments. Okay, so we have string instruments like guitar, piano is a string instrument. Let's see, we'll put examples. Example is piano, guitar. They're played by plucking the strings. I've got guitars behind me. I could pluck one for you, but for the time's sake, we won't do that today. Then you have woodwinds. And they have a wooden reed. And that's going to be things like an oboe, a clarinet, things like that. I don't think that says oboe. Let me look at the picture. I'm spelling oboe right. A clarinet is a reed. So there's like a little piece of wood, and you have to blow through the instrument to get the wood. That was right. I was thinking that was not right, but I was right. So that is an oboe. Okay. And there's a little piece of wood They use a small piece of wood and your breath. Okay, and that's how that makes the sound. The vibrations of your air blowing off the wood. Then you have percussion. Okay, and percussion, what's things like drums, um, the xylophone, those are played by hitting. Okay, and then the last one is brass. And those are things like, let's see. Well, I hit the wrong button. Brass. Brass instruments are things like a trombone, a trumpet. Those are my niece plays the trumpet. My nephew played the trombone and the baritone. But those are things like trumpet and tuba. They are brass. They're metal, and they're just you just blow, and your breath is what makes the sound. Okay, the other thing I want to add is about echolocation. Okay. Okay, so echolocation is what bats and whales use to know where they're at. And it's the same thing like sonar. They use sound waves to know where they're at. And the same thing with sonar. All right, and I'm just going to say same thing. All right, so, oh, I need to add one more thing that I forgot, and we'll just add it to the top right here. Amplitude, and that is how loud or soft something is. It's the volume. So, like if you have a baseline for a wavelength, so like the middle, this would be a soft volume. And then this would be a loud volume. Your wavelength is getting bigger and it's smaller when it's softer. All right, we will continue this all week and we will talk about sound. I've got a slide presentation to go through with you, not necessarily for you to do. All right, guys, make sure you copy these down.